Welcome to the third episode of the video series From Classical Mechanics to Cold Atoms, where I try to give you intuition on how to go from the classical to the quantum world using a single atom. Let's get into it. In the previous episode, we learned that the de Broglie wavelength is the parameter that tells us whether we are in the classical regime or the quantum regime, and that we can go from one to the other by changing the temperature. This also, with the expression shown here, tells us that in order to cool the atom, we need to slow it down. And for that, we need to use a technique called laser cooling. Here we consider an atom with one valence electron, shown here in blue, with an effective nucleus shown in purple. Effective nucleus just means that we're considering the nucleus of the atom plus all the electrons that are not the valence one. Then we can have an atom with energy E1, where the valence electron is in the inner orbital, or with energy E2, where the valence electron is in the outer orbital. And the energy difference is shown here. Here F stands for the frequency of the light that we can send to the atom to excite the electron. Then if we initially have an atom traveling to the right at speed v1 and we send a photon with frequency f to the left, this photon is going to be absorbed, and due to the absorption kick, the recoil, the atom is going to slow down a little bit and it's going to end up with velocity v2, which is smaller than the initial one v1. Later on, since the atom is not stable at energy E2, the electron goes back to its initial state and spontaneous emission occurs, meaning that a photon is generated in a random direction. Therefore, the atom ends up with a velocity v, which is between v1 and v2. What happens then if this process is repeated many times? Well, that's going to be the topic of the next episode.